Guys, cool it. Be quiet. Alright, we're going over Newton's laws of motion. And if you want to. Thomas, you don't have to talk. Thomas, next time you utter something, I'm writing you up. So how many of y'all have already seen Newton's laws of motion? Alright, so this should be familiar. We're going to go into a little bit more detail than you probably have already covered. So most people will know what Newton's laws say. Many people do not know exactly what they mean. You don't have to write this down. But they simply do not know, believe what they say. So what are Newton's laws of motion? The first law states an object at rest will stay at rest. An object in motion will stay in motion at a constant velocity unless acted upon by unbalanced force. Newton's second law states that force equals mass times acceleration. And Newton's third law says for every action there's an equal and opposite reaction. Nicole, would you close the door? So, the first law of motion is known as the law of inertia. This is it just repeated. An object at rest will stay at rest. An object in motion will stay in motion at a constant velocity unless acted upon by unbalanced force. Only thing you really need to write here is the first law of motion is also known as the law of inertia. So what is inertia? Inertia is the tendency of an object to resist changes in velocity, whether in motion or motionless. So an object that's sitting still has inertia. Anything with mass has inertia. So if you have mass, you're going to have some inertia. You're going to have some tendency to resist change in motion. These desks have mass. They're not going to start randomly moving. They're going to tend to stay still. If there was an earthquake going on, the floor or the ground would begin moving. We would see the desk start sliding around, but what's actually happening is the desk will try to stay still while the floor beneath it will move around and it'll appear like they're shaking and going around. When in fact they tend to stay put while the ground below them would move. A car going down the road at a certain speed tends to continually move at that speed unless some force such as friction were to slow it down. If you hit a baseball, it will continue flying through the air at whatever speed you hit it at. It's not until some external force such as air resistance starts happening with it does it actually begin slowing down. So looking at, for example, a golf ball, once airborne, unless acted on by unbalanced force such as gravity and air, it would never stop. So if you were to roll or hit a golf ball, it would continually move forever unless some external force such as gravity or friction from the air were to slow it down. By the way, I think I mentioned this before. It might be in our class. Is air a fluid? Well, is a gas a fluid? What does fluid mean? No, it does not mean liquid. Yes, a liquid is a fluid, but fluid is not liquid. It's like saying a truck is an automobile, right? A truck is an automobile, right? Is a car a truck? But a car is still an automobile. Automobiles cover both trucks and cars. Fluid is anything that flows. Does air flow? We have wind. We have wind, air flowing past us. So gases and liquids are both fluids. A fluid is just something that flows. So air resistance is known as a fluid friction. Just as if a boat driving through water is being slowed down by water resistance, both the water and the air are both known as fluids. So unless acted upon by unbalanced force, this golf ball would sit on the tee forever. Or after you hit it, it will continue moving forever unless some resistance or unbalanced force were to act upon it. You can if you want. If you were in space, such as if you were on the International Space Station, and they were to take a wrench and throw it, that wrench will continue moving forever because there's no air to resist its motion in space. It will either continue moving for all eternity throughout space, or it will eventually collide and hit the Earth or some other body. So until it actually interacts with the gravity of Earth or encounters some gas, it will continue moving forever. If you are in space without any air, if you were to take a pencil and spin it, it will continue to spin in a circle for all eternity until some force slows it down. So, why then do we observe everyday objects in motion slowing down and becoming motionless, seemingly without any outside force? It's because of friction. Friction pops up everywhere. So, friction is considered a force. There's multiple types of friction that I will go over here in a second. So, objects on Earth. Want me to go back? So objects on Earth, unlike the frictionless space the moon travels through, are under the influences of friction. So the moon is constantly circling around the Earth. It never slows down. Technically, there's some exceptions to this um, that we will not get into this class. But basically, the moon is constantly going to orbit around the Earth because there's nothing in space to slow it down. There are four main types of friction. So what is this unbalanced force that acts upon motion? Friction, and there are four main types. There is a sliding friction. This is when two surfaces are sliding on top of each other. Think of taking a box and pushing it across the floor. The flat portion of the box is rubbing against the flat portion of the floor, and this is generating friction. We also have rolling friction. This is when an object rolls over another one. Think of a bowling ball or the tires on a car. We also have fluid friction. Again, fluid both includes gases and liquids. So air is a fluid. It flows. So is water. Water is a liquid. It also flows. So air and water resistance. We also have something known as static friction. Static friction is the initial friction when moving an object. Have y'all learned about atoms and like bonds? So if you were to touch something, the atoms on the surface of that object and on one object and the atoms on another object, they temporarily bond together. These bonds are very, very weak. It doesn't take much force to break them, but you do have some amount of bonding going on, and you have to overcome this. This is the reason why, if I were to go over to that dresser and push on it, it probably won't start moving. The reason why it won't start moving is because the static friction is holding it down. Usually friction, all it does is resist the change. It slows things down. Such as that if I begin pushing a heavy box, it'll quickly slow down because of friction. Static friction is the initial friction you have to overcome to get it to start moving. So if you slide a book across a table and watch it slide to a rest position, the book comes to a rest because of the presence of a force. That force being the force of friction, which brings the book to a rest position. So the reason why when you slide something across the surface and it slows down is because of friction. In the absence of friction, so when you do not have the force of friction acting on something, the book would move forever. It will continually slide and never slow down. It will slide in the same direction because remember again, the first law talks about velocity. Velocity includes both speed and direction. So if an object is in motion, it will continue moving at the same constant velocity, meaning both that it will continue moving in a straight line and with the same speed. And of course, it will continue doing this until it reaches the end of the table, in which case the force of gravity would act on it and cause it to curve or change direction. So, in the absence of a force of friction, objects will move forever in the same direction with the same speed. So, let's go over some examples of everyday life that the first law applies to you. So, if you were to drive a car into a brick wall, you are in motion. Yes. If I get too far ahead, tell me to go back. I will. So, if you drive toward a brick wall in your car, the wall will exert a force onto your car. If you aren't wearing a seatbelt or you don't run into your steering wheel, you will continue moving forward at the exact same speed. So if you were driving 50 miles an hour and your car were to suddenly stop, you would go flying through the windshield at 50 miles an hour. By the way, out of curiosity, do y'all think it's safe to drive at 20 miles an hour without a seatbelt? Do y'all think it's alright to run at 15 or 10 miles an hour without a seatbelt? I know you should, but do you think it's safe? Alright. No, but imagine this. It's the exact same thing as running at 10 to 20 miles an hour. First of all, y'all know who Usain Bolt is? He can run at a top speed of 28 miles an hour, I believe. His average speed is like around 20 miles an hour. But if you were driving at 10 to 20 miles an hour, imagine running that fast. Running almost like Usain Bolt. And then run into a brick wall. Do you think that would hurt? It would be the exact same thing as being in a car going 10 to 20 miles an hour and the car suddenly stops and you rush into your steering wheel. Yes. And it hurt. So, it depends on how quickly the car stops. But, people have died in car crashes that were only 15 or 20 miles an hour. Because they ran into something and then their forehead hit the windshield at 20 miles an hour. And that's well enough to kill you. Usually, though, unless you hit something very sturdy, it's not going to stop you instantly. Like if you run into a small brick wall, your chances are your car is going to push through it. And you're going to break the wall, and it's going to slow you down ever so slightly slower than instantly stop. So you do end up slowing down slightly. But because of inertia, objects including you resist changing in motion. So if the car was going 80 kilometers an hour and it's stopped by a brick wall, your body will still keep going 80 miles per hour. You might have noticed this if you were to slam on your brakes and if you had something in the seat next to you not tied down, it was flung forward. That's because whatever speed it was going at, it stays at that speed. So this brings us to the second law. Force is equal to mass times acceleration. Acceleration is how quickly your speed is changing. Mass is how much matter makes up an object, and force is going to be a quantity that represents mass times acceleration. It's your weight, for example, is a force. It's how much force you apply to a scale when standing on it. So net force of an object is equal to the product of its mass and acceleration. F equals ma. So the quicker you accelerate, or the quicker you change your speed, the more force is going to be impacted on you. So if you're in a car and you're going 20 miles an hour, or let's say that you're running. Let's say you're running, and you run into a brick wall at 20 miles an hour. If you instantly stop as soon as you hit the brick wall, you're going to generate a lot of force because you stopped really, really quickly. Versus if you were to jump off of a building and land on a giant big balloon. The balloon is going to slowly cause you to decelerate. So, have y'all ever done the lake thing where they have that balloon and you jump? Yeah. So, when you hit the ground, you're probably going, or hit the balloon, you're probably going 10 or 20 miles an hour. But depending on how high up or how big it is, but you don't really feel like you're hitting with a big force because the balloon slows you down. So if your change in speed, your acceleration is small, then the force will be small too. If your change in speed, so if you go from 50 miles an hour to 0 miles an hour in a fraction of a second, and Thomas, wake up, keep your eyes open and watch. But if you go from 50 miles an hour to 0 miles an hour in a fraction of a second, that generates a large force. Also, if I were to drop a piece of paper on your hand, probably won't hurt because the mass is small. However, if I were to drop a giant big bowling ball on your hand or your foot, it would probably hurt a lot because it has a lot of mass. So force is controlled by both the product of its mass, how much mass there is, and acceleration, how quickly the speed changes. So when mass is in kilograms and acceleration is in meters per second, or meters per second, the unit of force is measured in newtons. 1 newton is equal to the force required to accelerate 1 kilogram of a mass at 1 meter per second. So if you had something that was 1 kilogram, and you were to increase its speed from 0 meters per second to 1 meter per second in 1 second, that would be equal to 1 newton of force. In SI units, we use newtons for force. Everyone good? I'm about to say it. Do y'all know what the Pythagorean theorem is? So why is it called the Pythagorean theorem? There's a guy named Pythagoras. So he is not the first person who came up with it. In China and a lot of Asian countries, they learned about Gogu, the Gogu theorem. Gogu came up with the Pythagorean theorem before Pythagoras. Gogu, Gougu. It's known in a lot of places as the Gogu theorem. In America, we give credit to Pythagoras, even though that's not it. In India, I forget who they give credit to, but Pythagoras is more commonly known in here, but in a lot of countries, Gogu theorem is the preferred name for that equation. That was the code word for the day. Let's do some examples. I've given y'all a new equation. Yes. Yes. So how much force is needed to accelerate a 1,400 kilogram car 2 meters per second per second? So we begin by looking at our equation. We're trying to solve for force. Our equation for force is equal to mass times acceleration. So we're looking for force. This is already set up. We can make a triangle out of this. So yes, F would go at the top, M and A would go on the bottom because they're multiplied. So again, we're going to be using this equation. It's going to be most of the math we do. So we have our equation. Let's look at our variables. Kilogram is a measure of mass. 2 meters per second it's going to be our acceleration. So our mass is 1,400 kilograms. And our acceleration is 2 meters per second squared. So plugging it in, we get 1,400 kilograms times 2 meters per second squared. And that's 2,800 kilogram times meter per second squared. Now, if our mass is in kilograms and our acceleration is in meters per second squared or meters per second, we can convert this to a new unit called newtons. We can rewrite this as 2,800 newtons. So a newton is equal to a kilogram times a meter divided by second squared. These two are the same units. They just didn't want to keep writing this over and over again, so they replaced it with the letter N. Note, this is a capital N, and all these are lowercase. Everyone good? Yes, but I think I'm going to keep it all in kilograms and meters per second. Because it's very so. What is the unit for mass in the United States? No, that is weight. That is force. It's slugs. That's weight. That's force. So pounds is it's technically called pound force. Is the equivalent of newtons, and mass is something known as slug. Um, have y'all ever heard of slugs? No. The unit of slug. The reason why you never heard it is because everyone hates the imperial system, and whenever we do force calculations, we convert over to metric usually. Inches, feet, pounds is the imperial system. Metric is kilograms, liters, centimeters, meters. We technically have something known as pound force, or foot pounds. Foot pounds is actually energy. But we do treat pounds as a force, which would be newtons, and we have created something known as normal pounds, which we usually don't represent. It's confusing. The imperial system's a mess. Metric system is way better because there's no unit conversions involved in the metric system here. Whereas if we used pounds and we used inches and feet, we would have to do a lot of conversion to solve the math. So net force is so if we have a mass of 2 kilograms, an acceleration of 5 meters per second squared, the net force would be 10. If we double the acceleration, so 2 kilograms and a mass of 2 kilograms and an acceleration of 10, we multiply these together to get 20. So if I told you that the net force was 20 and the acceleration is 5 meters per second squared, what would be the mass? It'd be 4 kilograms. So if I told you that the force was equal to 20 newtons and the acceleration was equal to 5 meters per second squared, then we can get our formula. F equals ma, our triangle. F equals ma, and we're trying to solve for mass. Mass is equal to force divided by a, acceleration. So that would be 20 newtons divided by 5 meters per second squared, which would equal 4 newtons divided by a meter per second squared. Just note that mass, this is really kilograms, so that'd be 4 kilograms. Again, this is basically saying what times 5 gives you 20. That's what this division is. So 20, so it's saying what times 5 gives you 20. Or another way of saying that, 20 divided by 5 gives you 4. Yes. So what would be the net force if your mass is 1 kilogram and your acceleration is 10 meters per second squared? It'd be 10 newtons. Make sure you put the appropriate units. So if mass remains constant and you double the acceleration, you also double the force. If force remains constant, doubling the mass halves the acceleration. So if you have the same force and you were to double the mass, it would half the acceleration. Let me show you that. So in our equation, we have force equals mass times acceleration. If this is held constant, so this stays constant, and if I double this, so if I double this, what times a double equals the same thing? In order for it to cancel out, you would have to half this. So if you double the mass, your acceleration will decrease by 2. Think of it like this. If you're pushing a very light cart in a store, and you push it as hard as possible, it's going to go flying really fast if it's empty, right? Now, if you fill it up with a large amount of mass, and you still push with the same amount of force, it's not going to go as far, right? Because it has more mass. If it's going down a hill, it's no longer having the same amount of force. Gravity is now also pulling it down the hill. It's not just your force. So Newton's second law proves that different masses accelerate the Earth. Huh? You can if you want to, I think. So Newton's second law proves that different masses accelerate to the Earth at the same rate, but with different forces. If you didn't know this, everything falls at the exact same rate. Everything falls with the exact same acceleration. So if you were to drop a car off the Empire State Building, and you were to drop a penny, or even a feather, if you were to drop a feather in a car, if you were to remove all the air, so there's no air resistance, both a feather or a sheet of paper would fall at the same rate as a large car falling off the building. Everything on Earth falls at the same acceleration. The difference, though, is which will have more force when it hits the ground. The feather hitting the ground or the car? Car, because the mass is different. So even though that they have different masses, they have different forces associated with them. Your weight is considered a force. That's the reason why you would have a different weight standing on Earth than on the moon. And you would feel weightless if you went into outer space. So the force changes, but the acceleration doesn't. We know that objects with different masses accelerate to the ground at the same rate. However, because of second law, we know that they don't hit the ground with the same force. So a heavier object would hit the ground with a much heavier acceleration. By the way, in case you didn't know, the acceleration on Earth is 9.8 meters per second squared, which means it's roughly about 10 meters per second squared. Which means if you were to jump off of a building, in 1 second you would be going about 10 meters per second. In 2 seconds, you would increase your speed by another 10. Technically more like 9.8, but 10 is a good approximation. Every second, you're going 10 meters per second faster and faster. Assuming there's no air resistance, you would keep getting faster and faster and faster until you hit the ground. And around 20 to 30 meters per second is about 50 miles an hour. Everyone good? So you might have heard that this is the myth that we will do this later, gravity. But no, I'll do it for you. So, well, I'll do it tomorrow. Y'all should be coming to class on weekends. Jeez. I'm joking. I meant next time. That's it for the day.